Hello, everyone. Okay, great to have you all here. My name is Mark Hoemmen, and I'll be speaking to you today about design patterns for error handling in C++ programs using parallel algorithms and executors. And before I get started, this talk will be, I'll speak for about 25 minutes. If you could please, I'll hold answering questions until the end. But please feel free during the talk to type in Remo in the Q&A section to add questions there. And if you could include the slide number or title when you ask the question, that would help me answer them. I'll answer questions at the end. Immediately after the talk, there will be an AMA, Ask Me Anything. That will happen in the same room, and I will just continue with the same stream and keep talking. So just if you're interested in attending the AMA, please just stay in the same room, keep connected, and we'll continue there. Thank you. And my name is pronounced, I included some IPA there, and my pronouns are he and him. So I have about 10 years experience after my PhD writing parallel C++ for science and engineering applications. My background is in parallel algorithms for solving large linear algebra problems. I'm really new to C++ standardization processes. My first standard committee meeting was at the end of 2017. And I just started a new job at Stellar Science in March of this year. Today, I'll tell you about how parallelism makes it harder to do error handling, to deal with errors. And specifically, C++ parallel algorithms and tasks make it harder to handle errors. I'll then talk about the message passing interface for parallel programming in a distributed memory sense, which has been around for about 3 decades. MPI experiences from MPI teach us design patterns to detect and handle recoverable errors. And I'll outline some of those towards the end of the talk. When I say parallel, I mean using multiple hardware resources, nodes, cores, vector units, SIMD units, to accomplish more than one work item at the same time in order to improve performance. Performance could mean latency, throughput, or responsiveness. Parallelism hinders error handling, and that's because parallelism relaxes execution order, and it does so deliberately to improve performance. I owe to Daisy Hoemmen, whom you might know, the distinction between parallelism and concurrency. Parallelism relaxes execution order to go faster. Concurrency constrains execution order in order to make it easier to reason about what's happening. When an error happens, it interrupts the normal flow of execution. And in order to handle the error, it constrains the order of execution. You have to change the control flow. Errors could actually lead to deadlock, which means waiting forever. For example, if one parallel worker drops out before a collective synchronization between multiple parallel workers, the other workers may wait forever. And the correct handling of errors requires communication. When I say communication, I mean either data movement or synchronization. They're really the same thing. Data movement implies causality, which implies synchronization. And we might need to communicate for a couple reasons. For example, we might need to stop other workers from waiting forever on us, or we might need to propagate and combine error information from other workers. Now, there's really no free lunch. There's no zero overhead solution to this. Error handling requires communication. Communication is expensive. It costs a lot, especially in modern computer architectures. Making C++ do it for you automatically will not be free. And so as C++ developers often want a zero overhead solution, if that's what you want, you, the coder, will need to handle errors. Now, standard C++ offers a few different ways to get parallelism, just in the standard. First are the parallel algorithms that are in C++ 17. These include algorithms like for each, reduce, transform, and sort. The first argument of these parallel algorithms is an execution policy. And that specifies the permitted changes in execution order from the normal sequential order. And for all of the execution policies currently in the standard, if you throw in your parallel loop body, in the element access function that you give to the parallel algorithm, terminate will be called. There are also asynchronous tasks. For example, C++ 11 has async. And when you launch an asynchronous task, uncaught exceptions in your task get captured, and waiting on a result throws the passed along exception in the future. There are also proposals to add more general asynchronous tasks. For example, there's P0443 Executors, and its companion paper, the Asynchronous Algorithms paper, P1897. And executors have a separate path of the so-called error channel for handling an ancestor task uncaught exception. There's also an algorithm when all, and when all allows a task to express a dependency on more than one task. So a task can depend on two or more or parents. And when more than one parent task throws, the when all algorithm captures only one of those exceptions. It drops the rest. So as you can see, two examples of how exceptions can cause trouble in your parallel code. I mean, a parallel algorithm, if you throw in your loop body, instead of the exception propagating as it does normally in a sequential algorithm, terminate is called. And in when all, if more than one parent throws, all but one of the exceptions are dropped. So you may argue, well, if I'm writing parallel code, I care a lot about performance. And so I shouldn't be having exceptions in my parallel code. I should have written my code not to throw. And that's an argument we can think about. Exceptions are for recoverable errors, really. If we have non-recoverable errors, maybe terminate is good. But let's think about the kinds of code, the code characteristics that can lead to us wanting to handle errors, that can lead to us wanting to deal with exceptions. I'll read this diagram, this big chart from the bottom up. And on the left side, I see what is the status of exceptions in that level of code. And on the right side, we see the typical kinds of things that that level of code might do. So at the very lowest level of parallel code, exceptions are not allowed, even if we catch them. You're just not allowed to throw or catch or do anything. And that happens in code that like explicit SIMD intrinsics or dialects of C++ for running on GPUs. Above there, there's a level of abstraction where exceptions usually indicate bugs, contract violations. That kind of code looks like tight, well-optimized loops. I've thought really hard about how to make the code go fast. And so any exception that I might encounter there means I made a mistake, I made a bug. But above that level of code, we often see code where exceptions that are not bugs, that are not contract violations, and other kinds of recoverable errors are more likely. This kind of code might call third-party libraries of unknown provenance. It might do input and output operations. It might do speculative computations. And I'll show you an example of code like that wants to live in a parallel loop in the next slide. This example is an algorithm called domain decomposition. It's from my background in solving large sparse linear algebra problems. Domain decomposition is an algorithm for solving a big system of linear equations, ax equals b. And in domain decomposition, we do that by decomposing the big linear system into many small linear systems called subdomains. We solve those small systems independently, and then we combine the results. Domain decomposition is an approximation, and so we may have to repeat this process until we converge, until we get close to the right answer. Now, domain decomposition is not foolproof. It might fail. And it might fail for any of various reasons. The entire problem might have no solution mathematically, or it might take too many iterations to get to an accurate solution. Or some of the small systems may not have a solution at all mathematically, even though the whole problem does. Or we might fail to solve the small systems for some reason other than their mathematical properties. For example, we may run out of resources. Now, there are other algorithms that we can use to solve big linear systems. These fallback algorithms, like a sparse LU factorization, can take a lot more memory and time. So we would prefer for domain decomposition to work, but still we do have a fallback. On the left, I show a sketch of how we might implement domain decomposition in the non-parallel case, so the pre-parallelized example. And we just wrap the whole thing in a try-catch. We set up for all the subdomain solves. We do a for loop over the subdomain solves. We solve each one in turn, and then we clean up afterwards to combine all the results. And no matter what solve throws, if any of the subdomain solves fail, we know that we need to fall back to a different solver. And so we just say that we fall back to a different solver. Now, on the right, I'm showing how we might parallelize this algorithm. Now, we've done two things to parallelize and to optimize. The first thing that we did is to use a fixed size memory pool. This is because memory allocation inside of a parallel loop can sometimes be slow. It kind of needs to synchronize if you think about it. And so here, I've used a fixed size memory pool to speed up that allocation process. And I've also replaced the range for loop on the left with a C++ parallel algorithm called for each. And I'm using the par unseek execution policy. That means parallel and unsequenced. So I'm allowed to execute the loop iterations in any order. In our domain decomposition, in our parallel domain decomposition algorithm, we need to be able to distinguish between two different possible errors. First, it could be that the memory pool is too small. If the memory pool is too small, well, we need to figure out how much additional space we need in the pool. We need to reallocate the pool, and then we need to retry domain decomposition. But there's another kind of error, and that could be the error in which it is mathematically impossible to solve one or more of the subdomain problems. In that case, we need to give up on domain decomposition and fall back to the slower solver. However, we have a bit of a problem. Inside of the parallel algorithm, any kind of throw causes terminate to be called. And that means that we can't have a try-catch that distinguishes between the different types of errors by catching different exceptions. So what do we do about this? We can't distinguish between the kinds of errors. So how do we tell what happened and recover from it? Hold that thought, and I'll talk to you a little bit about the message passing interface. The message passing interface, or MPI, is a C and a Fortran interface for writing distributed memory parallel code. It's a library interface. So you call functions, there might be macros involved in the C interface. MPI has been a standard for 3 decades. It unified divergent interfaces for distributed memory parallelism around the early 90s. The first version of the MPI standard was published in 1994, but it's an ongoing evolving standard. In 2015, version 3.1 came out, and version 4.0 is pending. People use MPI to solve enormous, huge problems on enormous computers. You can get millions-way parallelism with MPI. MPI is a stable interface. Code from the 90s just works. It has modest hardware requirements. You really just need some kind of computers hooked up to a network. You can run it on a Raspberry Pi cluster. You can run on all sorts of computers. And MPI cooperates with other programming models, for example, threads or for GPUs. Now, MPI is a distributed memory parallelism model. And the idea is that you start with P parallel processes. They have a fixed location in hardware. There's a fixed number of them, P. And so it's a little bit like your entire program is running in a parallel for each over the integer range from 0 to P minus 1. The processes are distributed. They do not share memory at all. And so in order for the processes to communicate, you as the programmer need to do something explicitly. And the main way that you do that in MPI is by messages. These are explicit function calls. You can call a function to send something, to receive something, or to communicate something altogether. And the calls are two-sided. All of the entities, all of the processes that participate must call the function. So if I'm sending, I need to call something, and you, the receiver, need to call another function that corresponds to my send. Messages can come in point-to-point form, send and receive, or they can come in collective operations like reduces, all reduces, scatters, and gathers. And on the right side of this slide, I show a diagram illustrating 4 MPI processes, and they're sending and receiving messages. The messages do not synchronize with respect to the collective communication. And you can see that process 3, when it sends, process 0 receives, process 0 and process 3 both need to do something. And all of the processes that participate in the collective need to call a function as well. MPI is hostile to error handling. I would call it a bit more hostile, especially for C++ developers, than even C++ parallel algorithms are hostile. MPI, in fact, deliberately punted on error handling compared to competing programming models such as PVM, the parallel virtual machine. MPI's goal was really to portability and performance. MPI wanted to run faster, and it wanted to do so in a wider range of computer systems. Especially the early distributed memory parallel computers were very primitive in terms of their capabilities and in terms of the kinds of things that their network and the processors could do. And so the goal was to run faster and to be able to run on all of those systems as well. In fact, the MPI equivalent of terminate in C++ is only best effort. So if you call MPI abort on one process, hopefully it stops all the other processes, but there's no promise that it does so. And if you have a C++ exception that's thrown and you don't catch it, and it percolates all the way up to the top, that's undefined behavior for an MPI program. And often in my experience is that if you have an uncaught exception on one process, it causes deadlock because the other processes are waiting for that process to do something that it never does. There are some ways around that. You can get the terminate handler to call MPI abort, but it's only best effort. And so because MPI is such a hostile environment for error handling, we library and application developers who use MPI have learned some lessons from that. And I think those lessons are good for C++ parallel algorithms and tasks. And so I'll present those lessons to you now. The first is to turn exceptions into values before they risk breaking control flow or percolating up without being caught. The second is to turn a parallel 4 whose loop iterations might fail into a reduction. And you can reduce on did everybody succeed? And you can also reduce on other information that you can use to help with reporting the error and or recovering from it. The third lesson is to prevent synchronization-related deadlock. If you find yourself needing to synchronize in a parallel algorithm or task, you could use that as an opportunity to communicate error state because synchronization and communication are really the same thing. And finally, a lesson from MPI is to exploit out-of-band error reporting. The first lesson is to turn exceptions to values and reduce over work items. In C++ 17 parallel algorithms, there's no good way to get an uncaught exception back to the caller. It just calls terminate, so you can't propagate that information. Well, what do? You turn that exception into a value, like an error code, by catching it and returning a value. You then reduce over those return values to tell whether all the work items succeeded. And you might do that by changing the algorithm. So instead of calling for each, for example, you might call reduce or transform reduce. Now, there are some algorithms that are not easily convertible into reductions. Sort is a good example of that. And I'll explain later how to handle algorithms like that. Now, if you're using executors tasks with a when all algorithm that combines the results from multiple parent tasks, the when all algorithm drops all but one exception from the parent tasks. So if you need information from the other tasks' exceptions, what you need to do is turn those exceptions into values. For example, via the let error algorithm that's described in 1897. And then your next task will reduce over those values, the transformation of those exceptions into values. So it's really just like the parallel algorithms case. I'll describe here how I can take the first attempt at a parallel domain decomposition in my previous slides, and I can use this reduce over error information technique to get it to recover from errors. So in this algorithm, I change it first so that instead of the solves throwing, they return a result. Result is a struct that has two fields. First, there's a status field, that's a bit field that explains why the solve failed. And the second value in the struct is the number of bytes that we needed from the memory pool. Whether we got those bytes or not depends on whether the solve succeeded, of course. So the solves return error information, and then we reduce over those error information, over the solve results. So I've transformed my for each algorithm into a transform reduce algorithm. And I include, in the large red box, I include this reduction that takes the two results and combines their bit fields using bitwise and combines the number of bytes needed using addition. And so if the solve failed because we ran out of memory, now we have the number of bytes needed total. And so now we have the new required pool size, and we can try again. Now, deadlock, getting processes to wait forever, is really easy in an MPI program. That's because the entire program is a parallel for each. And so you find yourself needing to communicate and synchronize more often than in C++, where you have parallel algorithms that are separate and have a fork join semantic. So in MPI, the entire program is a parallel for each. You find yourself needing to communicate more. Each involved process must participate in the communication operation. So in the example diagram on the right, I show the sequence 4 processes running. Process 3 sends to process 0. If process 0 throws an exception before it can post the corresponding receive operation, then process 0 will not participate in the send and receive. That could make process 3 wait forever on the send. The send will wait until the receive actually runs. There's a bit of a subtlety there that I can explain in the AMA later. And so process 3 could wait forever there. Also, process 0 could wait forever. Because if process 0 catches the throw but fails to post the receive, and then process 0 participates in the barrier, process 0 will wait for process 3 to wait on the send for process 0. Deadlock in parallel C++, as I mentioned, is perhaps less likely because the way that you write code is more small parallel region after small parallel region versus MPI where everything is a parallel region. But it's still possible. So for example, if you're using a thread barrier where every thread must reach this barrier before any of the threads may proceed, that's a way that you could have deadlock in parallel C++. An example of a thread barrier in C++20 is STD latch or STD barrier. Those can be implemented with an atomic counter where you start with the number of agents of execution, and each agent of execution decrements by 1 that counter, and when the counter reaches 0, all the threads know that it's safe to go on. A good use for a thread barrier is in managing a shared resource. For example, you may want to make sure that all execution agents have stopped using the shared resource so that a coordinator agent can release the resource or reallocate it, make it bigger. And so in this example on the right, agent 0 throws before it can participate in the thread barrier, and so all the other threads wait forever. And the way that we can avoid deadlock in code like this is by going through the motions. So we can think of a parallel loop body as a sequence of local blocks punctuated by synchronization. Always participate in synchronization. So don't throw and prevent yourself from participating in synchronization. Catch it, participate in the synchronization, but give each of those local blocks a bypass. If there's an error, do nothing harmlessly and pass along the running error state. This looks a lot like the error channel in P0443 executors, and there's a good reason for that. You can kind of think of it that way. You can also treat synchronization as an opportunity for error reporting. For example, if you were implementing a thread barrier using an atomic counter, starting from 0 instead of the STD latch example, each execution agent that encounters an error can add a big number instead of just 1 to that counter. And so if the final count is bigger than the number of agents, that would tell you that some error occurred. Now, the final technique that we've learned from MPI for handling errors is something that I call out-of-band error reporting. Here, when I say out-of-band, I mean asynchronous, or not synchronizing with respect to whatever else you're doing. MPI has this interesting function called a non-blocking barrier, MPI barrier. Now, that's kind of a funny phrase, non-blocking barrier. What does that mean? It means something like you check in, and when you're ready to wait on everyone else, then you can wait. So it's kind of a two-phase process. Now, collectives in MPI are not ordered with respect to other kinds of communication. So messages, it's not like a memory fence. It's different. Messages can cross over the barrier. Also, when MPI says non-blocking, it's really important to distinguish that from makes progress in the background, makes asynchronous progress. MPI does not promise anything about making progress in the background. Communication doesn't have to happen until you call a function that says wait or test until the thing is done. So it's a little bit like in the C++ standard async. If you don't specify a launch policy to async, the standard could decide not to do anything until you call get on the resulting future. However, you can poll to force progress in MPI. So you could start the barrier, and when you're ready to wait on the barrier, you can call test, 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 test until it succeeds. And MPI is required to make progress on that. And so in this case, we can use this non-blocking barrier technique to test whether an MPI process threw or dropped out of communication. I show that here in the diagram on the right. So the way that that works is, first, each MPI process runs some risky local work that might throw. On the right, I show this as this diagonally shaded blue diagram. It shows up a little funny on the screen for you, but it's kind of this blue region. And those blue regions aren't synchronized across the processes. So that's why you can see that they end at different times. Now, when each process finishes that local work, it checks in by calling this non-blocking barrier function. And so the different processes check in at different times. And then the processes wait on whether the other processes have finished. And they do that by spinning on the MPI test function with a timeout. The process can also do other work speculatively while spinning. If there's a timeout, you assume that the other process, some other process may have died, so you call MPI abort to stop the program. If the test succeeds, you know that all the processes have checked in, so they all made it safely through the risky work. In C++, the equivalent of out-of-band communication, or the generalization of that idea, is atomic updates. In C++, lock-free atomic updates do not block. So you can use them anywhere in parallel algorithms or tasks, and you could stash away some error information later and then read it when you're done. And this is a good thing to do in sort or other reduction or other algorithms that are not easy to transform into reductions. You can also use it if you don't want to pay for the reduction. So if errors are rare, it's not really a zero overhead abstraction to call it a reduction. It's true that atomic updates may hinder some kinds of compiler optimizations, but that may only be a concern if the loop is really too optimized for recoverable exceptions, so it's less of a big deal. So just to summarize, C++ parallel algorithms and asynchronous tasks make it harder to do error handling, make it harder to discover errors have occurred, and make it harder to recover from them. And so we can deal with that by using design patterns that MPI parallel programmers have developed over time. For example, we can turn exceptions into values. We can reduce over error information. We can avoid deadlock due to synchronization and use synchronization as an opportunity to communicate error information. And we can exploit out-of-band communication, such as atomic updates, to detect and report errors. And I'd like to thank my new employer, Stellar Science, for funding my efforts and giving me the opportunity to give you this talk. And we're hiring modern C++ software engineers. And thank you all for visiting. And just, I'm going to answer questions now. Let's see if you have any questions. Do you have questions? Oh, thank you. Yes, please post your questions in the Q&A tab. Thank you. Oh, they don't have any questions. Aren't you curious about the spelling of meep meep? They're not curious about the spelling of meep meep. I'm going to tell the story anyway. So Paul Julian was the background artist for the Roadrunner cartoon with Wile E. Coyote. And the picture you see on the screen is actually a real Roadrunner. That's what they look like. I live in Albuquerque. We have these in our yard. They come and visit us. In fact, one of them raised a chick in our front yard because there was lots of grass in which it could hide. And in the cartoon, the background artist for the Roadrunner cartoon spells the sound that the Roadrunner in the cartoon makes as H-M-E-E-P. Now you know. Awesome. And if you have any detailed questions, I'm just going to stick around for the next half hour, and I'm not going to change anything. I'll keep connected in the same way and stay in the same room. Oh, good. You have a question. How would one write a custom executor? I would recommend reading the Executors paper for that. I'm not going to give a tutorial on writing an executor. That's a little bit out of scope for this talk, but it's a really interesting question. I'm more interested as someone who writes parallel algorithms. I'm more interested in the programming model that's presented to me rather than implementing the programming model. I think that's also a very interesting question, but that's a little bit out of my expertise. Where is Stellar Science located? Stellar Science has two main offices. Our biggest and our home office is here in Albuquerque, New Mexico. And we have another smaller office in Virginia. And we have a lot of remote workers. We've been hiring through this whole time, and we're still hiring. And so if you're interested, get in touch with me. I think we have a little over 100 employees right now. But we've been around for about 20 years. Okay, well, looks like the end of my half hour. As I said, I'm going to stick around here for the AMA. Thank you all for attending. If you want to go to the next talk, I don't want to stop you, but feel free to stick around and ask me questions. Thank you. Oh, good. Here's a question. Where can we get in touch with you? I am going to type my email address in the chat. You can also find me in the Slack channel. That's how you can reach me in the Slack channel. Personally, here's another question. Personally, I like how std async does error handling. Is the reason it doesn't apply here because you're going from 1 to n tasks and you need to aggregate the errors? I'm guessing that's referring, well, I guess that could refer either to when all or to the parallel algorithms. So if you're interested, there was a proposal to combine exceptions from multiple executing things. I think that was P0797. But yeah, that's the main issue. It doesn't really apply here, is that you have to aggregate the errors. That's exactly right. And it's not really clear how to do that. When all currently is, as the proposal stands, drops all but one of the errors. But you may not want to do that. And a lot of times, in order to recover from the error, you need to collect information from the errors. It's not enough to know that an error occurred. You need to know something like, well, I needed more space in my memory pool, but how much more space do I need? And so if you just drop exceptions, then you lose the opportunity to combine information that you would normally get from seeing all the exceptions one at a time. Awesome. If you like, I can describe an example of, oh, I have material for the AMA. I could just talk at the room if you like. Would that be boring? Somebody write in the chat whether you want me to keep talking or be quiet. There's silence. Oh, that's frightening. Okay. Keep talking until someone asks a question. Fantastic. Okay, I'm going to do that. Keep going, please. Okay, at least my volunteer and another person said keep going, so I will keep going. Yay, okay. So if you like, I can describe an example of this, how did I call it? Going through the motions error handling pattern. And so the going through the motions error handling pattern, I'll back up to the slide that talks about that. And in my particular case, I was working on a sparse matrix library, a library that dealt with very large matrices and graphs. And they're sparse means that most of the entries are 0, so you don't have to store them, but you still need to store some of them. And it's a big parallel library that uses MPI and threads and GPUs and all sorts of things. And the issue was users have the ability to construct a sparse graph, more or less, an adjacency list, where the graphs and matrices are kind of the same thing. And so users would distribute the rows of the graph over parallel processes, parallel MPI processes. And so my process is not aware of some of the graph. I can't see it. I don't even know about it. I just know how big my graph is. And I know that there are some number of other processes that have part of the graph. And when users construct the graph, they specify the indices to fit in each in the adjacency list. These correspond to columns of the sparse matrix. And the problem is, when I do that, I don't necessarily know if those column indices are valid, because they may correspond to rows or entries on remote processes. So I'm not able to check the user's input for errors until I do some parallel operation, until I do some communication. And it's an elaborate operation. It involves evaluating a distributed hash table to figure out who owns, what MPI process has those indices, and then I figure out by talking to that process if they're valid. And so I can't actually report errors until I've gone through a bunch of communication. And I might discover the errors early on, but the other processes don't know about the errors, and so I have to keep going. That was a motivating example for me. Oh, there are some questions. Hi, Mark. I'm curious to know the statuses for the MD-span, MD-array, and BLAS proposals. Do you anticipate they will land in C++ 23? I'm not sure about MD-array. MD-span, I know Christian and Daisy and the others are working that really hard. So I'm pretty confident about C++ 23 for MD-span. For the BLAS proposal, I really am not sure. We need to do some more work on our BLAS proposal. If you're not familiar with that, I'll type the BLAS proposal as P1673, and that's a linear algebra library proposal for the standard. And it was based on the BLAS, the basic linear algebra subroutine standard, which was standardized around 2002. Do I anticipate they will land in 23? It's hard to say. I think some people have brought up some questions because our proposal is proposing standard algorithms, additions to standard algorithms. It's reasonable that people are wanting us to do a concept-based design, and there are some other papers that attempt a concept-based redesign of the numeric algorithms. I have feelings about that I can share separately, but so I think our design may undergo some revision, and there are also questions that people have had. So I think there's more work to do on our proposal. There's another proposal, 1385, which is more of an expression-based, a plus and times-based proposal. I'm not sure quite of the status of that. I know Bob Stiegel and Guy are working really hard on that one too. So it's uncertain, especially with all the uncertainty about meetings. It's really hard to say. Is there a reference implementation for the BLAS proposal? Yes, there is. And I think it can be found. I will find you a link. BLAS. And since I've changed jobs, I have to resolve some of the issues with licensing. But it's not under my control. It's under Sandia's control. So here's the link to the reference BLAS implementation. Have I seen MPI user-defined operations used for collective reduction of exception or error values in C++ with MPI codes? That's a very reasonable thing to do. So if you're not familiar with how MPI works in the C++ parallel algorithms, or just the C++ algorithms, in a reduce or an accumulate, you can use a custom plus, a custom combine operation to combine two results. And in MPI, you can do the same thing. You have to do it in a C or Fortran way, but it's the same idea. So I haven't needed to do this to make a user-defined operation to reduce over error codes, but it could be a reasonable thing to do, especially if you have a struct with more than two values of error information to gather. It would be very reasonable to do. And in my previous project, I was working in a C++ library that had a wrapper around the C binding for MPI. And so it was invisible to the programmer to create user-defined operations, reduction operations. So I hope that answers your question. The short answer is, while I haven't seen it, I think it's a reasonable thing to do. Awesome. Okay, I'll wait a little bit for a question. And while I'm waiting, I can talk about things. I could talk a little bit about MPI has a very fun thing where the messages are, MPI messages, there are rules about synchronization that, and if you're familiar with some of the memory ordering stuff in the C++ standard, it's kind of a familiar story. But I like studying the MPI standard and how messages synchronize because it's a little bit easier for me to visualize messages in my head. I can think about messages a little bit easier than I can about loads and stores, even though they're really the same thing. I think it's helpful to have that duality, to be able to go back and forth between them. And so some of you may have seen Hans Boehm and Paul McKinney's talk earlier today about the out of thin air problem with relaxed memory operations. And in MPI, the equivalent of that would be if one process sends two messages to the same process and they get reordered. And MPI actually forbids that. If I have process A and I send two messages with the same communicator and tag to process B, MPI is not allowed to switch the order of those two things. You can imagine how they might implement that with some kind of counter or something, but that's forbidden in MPI. But MPI, a lot of these issues have come up because more recent versions of MPI have introduced a one-sided model, which is like a global shared memory, not shared memory in the same sense that the C++ standard has, but like a partitioned global address space kind of shared memory. And there you have to think about things like synchronization and how the order of operations and what kinds of atomic operations you're allowed to do to the same memory location. But with MPI, because it's a more general model, it's not necessarily true that operations will complete until you do something. So you may have to do something explicit to make things complete. Oh, there's a new Q&A. What are some of the best libraries for linear algebra with a modern C++ interface? In terms of parallelism, I don't know. There are many of them, but and a lot of them rely on parallelization underneath. So Eigen, for example, and a lot of libraries will call a BLAS implementation underneath, and the BLAS may itself be parallel. So the BLAS may be vectorized, it may use threads, it may even use the GPU. And a lot of code relies on this. I know that people at the University of Tennessee, Knoxville are working on more modern interfaces for parallel linear algebra. A good example of that project would be Slate. And that kind of evolved from Magma. But I think there's also a question of what does it mean to have a modern C++ interface? Some people think of that as, oh, they want to be able to go A plus B, and they want to be able to make algebraic, they want to do algebra on matrices and have it and write the math like they would on the whiteboard. And for a lot of my career, I've been an implementer of linear algebra libraries. And so I have no use for that because it might allocate, it might do all sorts of things. If I say C equals A plus B, C might have a different parallel distribution than A or B, and that operation has to redistribute data. It's a familiar problem if you know a little bit about the high performance Fortran HPF effort in the 90s. And one of the reasons why it had so much trouble is because it was very easy to write slow operations like that. So I'm not necessarily so eager to have the interface be so much like math you would write on the whiteboard, but other users really want that interface. So I'm not sure if that really answers your question. There are a lot of libraries out there, but I've been focusing less on the higher level interface and more on the implementation of the library. Okay, next question. Is there any discussion of using C++ coroutines and MPI non-blocking operations? Why do you want pain? Okay, sorry. That's a really fun question. I think I would want an expert on networking to talk more about that, but it's really important to remember that MPI non-blocking operations, there's no promise of asynchronous progress. And so you have to be really careful about that. There's an implication of polling if you wanted a portable implementation that called MPI. I think if you wanted to deal with this problem in a more comprehensive way, you would want an MPI binding, you would want a C++ binding for MPI. And that's the kind of thing where you go to MPI standard meetings. MPI has been a really successful standard because it's worked so well and it's been supportable and people have been able to get reasonably good performance with it. But if you really want that tight integration with the C++ language, I'm not sure if the existing bindings to MPI can give that to you because of the semantics of non-blocking operations and things like that. Okay, next question. What's the biggest challenge for creating a standard library for linear algebra? Pleasing everyone. I had mentioned that some people want a high-level interface where they can say C equals A plus B. And some people want total control over memory allocation and parallelization. Around 15 or more years ago, you might be familiar with the LAPACK library. It's built on top of the BLAS library, and LAPACK implements matrix factorizations and other kinds of matrix operations. The LAPACK library at that time switched from Fortran 77 without dynamic memory allocation to a subset of Fortran 90 or 90X. And at that time, the LAPACK developers polled the users to ask, hey, how do you feel about dynamic memory allocation for Scratch? And most of the users said, no, we do not want dynamic memory allocation. Whereas if you're a user of Eigen or Armadillo library or uBLAS, a library like that, you don't really care. You just want to do C equals A plus B. So I think the biggest challenge is the scope of the library. And with our proposal, 1673, we said we're not interested in the high-level interface. We're just not going to go there. Our goal is to provide the implementation layer for such an interface. And so I think the biggest challenge is deciding on scope and deciding that there's going to be some users that you're not trying to serve, and that has to be okay. Cool. For modern API, one of the basic requirements, I think, is not having to use raw pointers. Yes, raw pointers are bad. I do have a raw, at the beginning of my talk. Yeah, you should issue raw pointers because they're pointy. But seriously, in our proposal, I think if you're wrapping the BLAS, we have a paper called 1674, and it describes if you encountered the BLAS and you were a C++ developer, what would you do to wrap it? And getting rid of the raw pointers would be the second thing you would do. The first thing you would do, the third thing you would do. The first thing you would do is get a C interface. The second thing you would do is get rid of the void star. The third thing you would do is get rid of the raw pointers. So yeah, absolutely. Cool. So I think we've got about 2 minutes left for the AMA. If you have any more questions, now's the time. Otherwise, you can reach me here or on Slack, or you can email me. And I'll be happy to answer your questions. And I'll just stick around until time is up. I'm going to show the Roadrunner because Roadrunners are cute. Oh no. Here we go. Oh, there's a question. Okay, good. Do I have experience working with SIMD intrinsics for linear algebra? Are you aware of good resources for learning more about how to do so? I have a little bit of experience with that, with SIMD intrinsics. I've done them actually more generally in physics simulation. And there the goal was to do outer loop vectorization so that we could solve, it was a finite element simulation. And so the elements are, you can think of them as little matrices or little problems. And for outer loop vectorization, each lane of the SIMD was a problem, an element of the problem, or an entry of the little matrix. We've thought about that. Certainly, the Cocos project has thought about that. So Cocos, you might know about. One of the Cocos libraries is a linear algebra library, and they have batched linear algebra operations. Batched. And the idea there is that you can do outer loop vectorization across linear algebra problems. And I think that's a really good way to solve it. So and a lot of vendors have that too. Intel MKL, NVIDIA's cuBLAS, other libraries have outer loop vectorization libraries. And I think that's a great way to get the most vectorization and parallelism out of a linear algebra problem. So that's where I've had the most experience working with SIMD intrinsics. I know Cocos developers have their own SIMD library, and they've been in dialogue with the SIMD technical specification proposal for the C++ standard. And I think all of these people have a similar background and interests, and they're interested in driving this into the standard. So I don't know so much about good resources, but there are certainly good libraries where you don't have to worry so much about typing SIMD intrinsics or SIMD expressions. You could just let the library do it for you. Is that kind of a helpful answer? I hope so. Cool. Okay. Well, I don't want to keep all of you. If you want to get in touch with me, please use either Slack or Remo or the email address that I gave. And I really appreciate all of you for coming to my talk. Thank you so much.